Planet Earth, a seemingly solid sphere, is a dynamic, ever-changing system. From the highest mountains to the deepest ocean trenches, our planet is in a constant state of flux. Beneath our feet, massive tectonic plates are constantly shifting and grinding against each other. These colossal slabs of rock move at a pace of mere centimeters per year, yet their impact is profound. These movements, though often imperceptible, are the driving force behind earthquakes, natural phenomena that can reshape landscapes and devastate civilizations in a matter of seconds. The energy released during an earthquake can be equivalent to the detonation of thousands of nuclear bombs. From minor tremors to catastrophic events, earthquakes remind us of the immense power that lies beneath the Earth's surface. They can topple buildings, trigger landslides, and even cause tsunamis, leaving a trail of destruction in their wake. They have been shaping our planet for billions of years, playing a pivotal role in the formation of mountains, oceans, and continents. The Himalayas, for instance, were formed by the collision of the Indian and Eurasian plates. They are a testament to the immense energy stored within the Earth and serve as a reminder of the delicate balance that exists in the natural world. This energy, when released, can alter the course of rivers, create new landforms, and even affect the Earth's rotation. Understanding earthquakes is not just about comprehending a geological phenomenon, it's about recognizing a force that has shaped our planet and continues to influence our lives today. The study of these forces helps us appreciate the dynamic nature of our world. The study of earthquakes, known as seismology, has made significant strides in recent decades. Researchers use advanced technology to monitor seismic activity and gather data that can help predict future events. Scientists can now measure the magnitude, location, and depth of earthquakes with remarkable accuracy, providing crucial information for disaster preparedness and risk assessment. This data is vital for designing buildings that can withstand seismic forces and for planning emergency response strategies. However, despite these advancements, predicting earthquakes remains a complex and elusive goal, and the destructive potential of these events continues to pose a significant threat to communities around the world. The unpredictability of earthquakes means that preparedness and resilience are our best defenses. As we delve deeper into the science and history of earthquakes, we gain a better understanding of our planet's dynamic nature and our own vulnerability in the face of its immense power. This knowledge empowers us to take proactive measures to protect ourselves and our communities from the inevitable forces of nature. To comprehend the awesome power of earthquakes, we must first understand the forces at play beneath our feet. These forces are not just random occurrences, but are deeply rooted in the dynamic nature of our planet. Picture the Earth's outermost layer, the lithosphere, not as a single solid shell, but as a jigsaw puzzle of massive plates. These plates, known as tectonic plates, fit together in a complex and ever-changing mosaic. These plates, constantly in motion due to the heat emanating from the Earth's core, interact with each other in various ways. The heat causes convection currents in the semi-fluid asthenosphere beneath the lithosphere, driving the plates to move. They collide, separate, or slide past one another, generating immense stress along their boundaries. This stress accumulates over time, creating potential energy that is eventually released during an earthquake. These boundaries, known as fault lines, are where most earthquakes occur. Fault lines are essentially fractures in the Earth's crust where this stress is concentrated. When the stress along a fault line exceeds the strength of the rocks, a sudden rupture occurs. This rupture is the breaking point where the accumulated stress is released. Imagine snapping a twig. The built-up tension is suddenly released, causing the twig to vibrate. This is a simple analogy to understand the sudden release of energy during an earthquake. Similarly, when rocks along a fault line break, they release energy in the form of seismic waves that travel through the Earth, causing the ground to shake. These seismic waves are what we detect and measure during an earthquake. This shaking, the hallmark of an earthquake, is what we feel on the surface. The intensity of this shaking can vary greatly depending on several factors, including the depth of the focus and the distance from the epicenter. The point within the Earth where the rupture occurs is called the focus or hypocenter of the earthquake. This is the origin point of the seismic waves. The point directly above the focus on the Earth's surface is called the epicenter. This is typically where the shaking is felt most strongly. Seismic waves radiate outward from the focus, decreasing in intensity with distance. These waves travel through the Earth's layers, losing energy as they move further from the source. This explains why the shaking is usually strongest near the epicenter and weakens as you move further away. The energy dissipates, reducing the impact felt at greater distances. The magnitude of an earthquake, a measure of the energy released during the rupture, is typically measured on the Richter scale. This scale helps scientists and engineers understand the potential damage and energy involved. This logarithmic scale means that each whole number increase on the scale represents a tenfold increase in wave amplitude and about 31.6 times more energy released. This exponential increase highlights the vast differences in energy between earthquakes of different magnitudes. For instance, a magnitude 7 earthquake releases about 31.6 times more energy than a magnitude 6 earthquake and 1,000 times more energy than a magnitude 5 earthquake. This dramatic difference underscores the importance of understanding earthquake magnitudes. Understanding the mechanics of earthquakes, from the movement of tectonic plates to the propagation of seismic waves, is crucial for assessing earthquake hazards, designing earthquake-resistant structures, and ultimately mitigating the risks associated with these powerful natural events. This knowledge helps us prepare and protect our communities from the devastating impacts of earthquakes.